Hello everybody, I hope you're doing well. Welcome back to another video in our Introduction to Calculus playlist. So in the previous video, we have gone over the idea of limits and how we can leverage various techniques such as variable substitution, conjugates, factoring, and properties of special limits to be able to solve various problems using limits. In this video, I want to kind of take a step back at the analogy we have established in the beginning of this playlist. And you might recall that we've talked about hiking, right? And I've kind of drawn a picture, right, of, an elevation versus time graph. So at a certain time, what elevation are we at in our hike? So here's an example of such a graph, right? Might have a hike that goes like that. Then, you might be coming back down. Um, let's make this a little cleaner though. So a graph of elevation versus time might look something like this. So let's say this was our hike, right? We've already talked about the idea of limits as, you know, in the context of this analogy as at this particular at this particular time t right here, right? What is the elevation we were at? So this would be f of t, right? So how do we write in mathematical terms the fact that as we approach this time t, the elevation approaches this value f of t? And we talked about the limit as a formal mathematical way to describe that very thing. But if all we had were limits to analyze hikes, right, then we would only be able to tell, right, what value the elevation approaches at a given time t, right? And the hike could be any looking curve like this, right? But this isn't really good to describe the hike, right? Another thing we might want to describe about the hike is, the rates of increase and decrease. So you might say, oh, well, at this point, I'm having a decrease in the elevation, and at this point, I have an increase in the elevation. And at this point, I have another increase, right? And another decrease. Let's take the example of a decrease, right? So here we have a decrease in elevation, but you might also argue right here we have a decrease in elevation. I'll mark these intervals in orange. So right here we have a decrease in elevation just by looking at the picture. And right here we also have a decrease in elevation. And you might ask me, well, one thing we could analyze is that the decrease in elevation is a little bit slower here, but the decrease in elevation is a lot more drastic right here in your curve. And I would definitely agree with you from looking at the picture, but what if we didn't have a picture, right, of this curve? How are we going to make sense of, how the elevation increases and decreases in our hike, right? And how can you tell me that oh, this elevation decrease is slower than this decrease in elevation, right? How can you know that other than saying, oh, the picture looks like that, right? We need some sort of a tool to be able to tell us, right? The decrease in elevation right here might not be as drastic as the decrease in elevation here, for example, in this hike. So because we want to analyze the change in elevation, the limit is not really going to help us in this context, right? Because the limit can tell us when we approach a given time t, the value of the elevation approaches this value called f of t. We need a way to analyze the change in elevation, you know, at a given time. So more precisely, wouldn't it be great if we had a tool to describe elevation change at a time t, right? And you might be thinking that, okay, so elevation change at a time t. So you're asking that we need a tool that can say at a given time t, what is the change in elevation, right? And you might think that I'm crazy because how do you know the instantaneous rate at which the elevation changes at a time t? Don't we need 2 points to be able to determine the rate of change? Just like in math, we've been taught in algebra that we need 2 points to determine the rate at which something changes. And I will be like, hold your horses, hold your horses. There is a way where we can describe, the instantaneous change in elevation at a time t. And you are right that we need 2 points to determine a change, right? Just like we need a time after and a time before to describe the change in a quantity. Now, how are we going to do this? Well, let's draw a simpler version of this hike down here. So we have the elevation versus time graph. And I'm going to make the curve a little bit simpler, right? All right, cool. So we have this curve here. And what we want to do is we want to figure out at this time t, what is the change in elevation, right? So at this time t, what is the change in elevation? And we need somehow a way to take one point and kind of convert it into 2 points, right? So we need a way to identify another point that we can use to say what is the change in elevation. And if you think back to math, right? If we had, a curve like this, right? And we had, you know, a point here and a point here. We can definitely take the rate of change between these 2 points, right? It's a matter of using the slope of a line, right? And we know that the slope equals the change in y over the change in x. So now how do we connect that to finding the rate at which the elevation changes at this particular time t? And this is the knowledge we have to find rate of change using the slope quantity. And the catch is we can do it, but it comes with identifying the second point. And we need to identify the second point in a very, very smart way to kind of get this instantaneous rate of change in the elevation. And how are we going to do this? Well, let's take this point, for example, in blue, right? I'm going to use this point in orange to identify a second point. So let's say the second point was right here. Okay, now that we know the elevations at these two values right here, let's say this is you know, V1, and this guy right here is V2. So these are the values of the elevation at these points, and this is going to be T2. So we have, the coordinates for the blue point and the orange point, and now we can take the rate of change because this would be the slope of this line shown right here, right? In orange. So that should be pretty easy. But this is not really instantaneous. And also, how do we identify this second point, T2? You might think that, hey, Karthik, you drew this point randomly on the grid, right? How are you supposed to know what the second point is? Is there like a formula for it? And my answer to that is there's really no formula for finding the second point. But I think the more interesting thing to observe is what we can do with the second point. We know this first point, right? This first point is kind of fixed. But what we can do is we can try moving the second point as shown. Consider the following. Let's say this T2 point, right, happens to be moved right here, right? And now we have this blue and yellow point, right? And this is now T2. So let me erase this orange right here. And this value V2 is going to kind of get moved up. So V2 would be more like right here. And now if we draw the line, I'm going to do this in green. So the line between this blue and yellow point now becomes something like that in this very rough drawing, right? But you can see now the difference between this orange line and this green line is that in the orange line, this line doesn't look like, the instantaneous rate of change in elevation, right? This is just taking, this orange point might be a little bit too far out. But if we look at, the line between the blue and yellow points and we take the rate of change, we can see that this line is kind of getting a bit close, right, to what's the rate of change, right, at this blue point. And in fact, if we make this yellow point closer and closer and closer, this green line is actually going to become a very better and better approximation for how is the rate of elevation changing at this time t, because we are going to move this yellow point closer and closer and closer. So we have a smaller and smaller window to base our rate of change on. And in fact, let's let's actually do that in a blown up version of this picture right here. So I'm going to move down here and have a more blown up drawing. let's say this was our elevation v time, right? And let's put the blue point right here. So this is going to be t1, and this is going to have a value f of t1. So this is like the v1 in the earlier picture. And we're going to have this second point, right? Let's say it was at first right here, right? So the line we're using to approximate the rate of change in the elevation at t1 is going to be this orange line right here, which is sort of a, decent approximation, but we could do better, right? And now let's say we have this yellow point that is moved up here, right? Now the yellow line right here is a bit better, right? There is a bit of improvement, but we could do a bit better. So let's move the yellow point. Let's have this orange point right here be kind of right next to this blue point. And if we draw the line right here, you know, the orange line is going to look more something like, let me clean the drawing up a little bit. The orange line is going to look more something like that. Yeah. So you can see right here in this orange line, right? We're kind of, intersecting this curve right here, this elevation versus time curve, just at the blue point, right? And what we're doing is we're taking this orange point, this is going to be t2, and this is going to be value f of t2. This f of t2 value is getting really, really close to f of t1, and this t1 is getting really, really close to t1. And the closer we make t2 to t1, the closer our second point is going to be next to our first point. And now we can take a rate of change because we have 2 points, and the 2 points are really close to each other. And that will give us the instantaneous rate of change at t1 for the elevation. So what is the summary of what do we discover here, right? Well, we discovered the following, right? Choose a second point very, very close to the point we want rate of change at. So we've discovered that if we choose the second point such that it's kind of very close to this blue point right here, which is what we want to take the rate of change of, then we're going to get a better and better approximation of the rate of change and elevation at T1. And now that we discovered that, we actually now have a tool for us to identify, you know, what is the elevation change like, at certain times in our hike, which gives us a little bit more power to describe beautifully what is the hike like from start to end. But we have one lingering question left. How do you know how close is close enough for this orange point? Is there a way to is there like some given bound of some sort that somebody created that can tell us, you know, choose a point, maybe five, maybe 0.1 millionth unit away from this blue point, and we'll have a good enough approximation. Is there like some sort of written rule like that? And that's a fair question to ask. And the answer is there is no written rule, right? Nobody can really write a blank slate saying that, oh, for functions like this, right, in green, we have to choose a point that is 1 millionth of a unit to the left and or right of this blue point in order to get the instantaneous rate of change. Nobody has a rule like that. But we do know something, right? What we did discover is that when we move the second point closer and closer and closer to this blue point, we are approaching, keyword here, we are approaching an approximation for the rate of change in elevation at this blue point at T1. So because of the keyword approaching, you might be wondering, wait a second, can't we just use the limit to kind of figure out what is this instantaneous rate of change in elevation at this blue point? And the answer is yes. So let me write this in yellow. So the realization is use limits to help us get instantaneous rate of change. So now the limit can help us give a proxy for at t1, what is my rate and elevation? And now we've kind of taken the fact that to find the rate of change, we need 2 points and used and manipulated the second point in a way such that we can get an approximation for what is this rate of change at the single point. And now, how are we going to formalize this, though, in some sort of notation? We have this realization right here, and we have this discovery with the second point, and how we can move the second point closer and closer and closer to this first point right here in blue to get this instantaneous rate of change at t1. So how are we going to convert this realization into a mathematical notation? Well, we'll have to introduce some sort of convention. So let's do that real quick. So I'm going to draw this function right here, right? Let this graph be f of x, right? So let y equal f of x as our function. And suppose we want to take what is the rate of change of this function, right, at this blue point right here. Let's call this blue point x, and the value that it'll take is f of x, right? And we want to take the second point kind of some unit like far from x. So let's call the second point right here, right, this orange point. And this orange point is going to be h units, right, to the right of x, right? So this point here will be x plus h, and thus this value here will be f of x plus h. And what do we discover? Well, we discovered that when we move this orange point closer and closer and closer to this blue point, then we know this separation distance right here, h, right, is going to approach 0, right? Because this orange point is going to be closer and closer and closer to the blue point. So we know here that h is going to approach 0, right? And when h approaches 0, then we're going to get an instantaneous rate of change of f at this blue point. And the line will look something like this. So we're going to get this nice tangent, right? This nice tangent line to f at x. And this is all accomplished by moving this orange point closer and closer to the blue point, so that the line between, this blue and orange point is going to become more and more tangent, right? And that this line in green will intersect f only at this blue point and nowhere else. So that's what we mean by a tangent. So we have the limit as h approaches 0, right? We know that that's part of the equation. And now we want to identify what is the rate of change, of a line going through this blue and orange point. Well, it's going to be, the change in y over the change in x. But what is the change in y? Well, it's going to be this y value minus this value, right? So this is going to equal the limit as h approaches 0 of f of x plus h minus f of x. And then what is the change in x? Well, the change in x is going to be this x value minus this x value. So this will be x plus h minus x, which is h. So this is going to be, so the approximation for this tangent line slope in green is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. And this, my friend, right here is the fundamental tool that we have in order to find instantaneous rate of change at a given x value. Now, what is this quantity called? Instead of us, saying instantaneous rate of change every single time we talk about this quantity, we need to give it a name. And the name we're going to give it is called a derivative. So this is AKA the derivative. So in order to find the instantaneous rate of change, of this function f of x at this blue point right here, we need to essentially take the derivative of the function f at x. And how are we going to do that? We're going to use our tool right here. We're essentially solving this limit problem based on the realization that if we take a point that's very, very close to x, right, we can take a rate of change, right? We can take the slope of the line and move the second point really, really close to this first point in order to make this line more and more tangent. So let me write the limit definition down below in a nice presentable manner. So this will be the limit as h approaches 0 of f of x plus h minus f of x over h. So this is the definition of the derivative. And you might see that this definition is only one of many possible definitions. This formulation is one formulation, and there's another formulation you will come across where it goes something like this. The limit as x approaches c of f of x minus f of c over x minus c. Now, how are these two definitions the same? Well, it all comes down to a matter of notation, right? When we draw this graph, right, and we have this function right here, we can simply call this blue point, right, c, and this value here is going to be f of c, and then we have this second point right here. Let's say the second point is at x, right? Sorry. So let's say the second point right here in orange is at x. So we know that this value here is going to be f of x. And now we want to move this second point right here really, really close to c, right? So think about what happens. This distance is just going to be x minus c. So we want to take, the limit as x minus c approaches 0 of f of x minus f of c over x minus c. And the thing here is that we're still taking the slope of, this line right here shown in green. So we're still taking the slope of this line right here between the blue and the orange point, but our limit is formulated like this. But what else, another way we can state this limit? Well, when x minus c is approaching 0, we can simply say that x is approaching c, right? Because when we move this orange point here closer and closer to c, we know that x is approaching c. So that's why this limit right here can be formulated to the limit as x approaches c of f of x minus f of c over x minus c. So because of this formulation and equivalence in the limits, that's why you will see that another way of expressing the derivative is through this limit definition. And it's good to kind of know both and be able to convert between this limit definition and this limit definition right here. So basically in this video, all we've really gone over is a derivation or a methodology to come up with a tool in order to identify rates of change at given points in a function in an quote unquote instantaneous manner. So that's a wrap for this video. In the next video, we will go through an example where we actually apply this limit definition to see for ourselves with a tangible example, what is it like to construct or compute an instantaneous rate of change of a function at a given point. And through that, we can start coming up with methods or rules to help making, this task of finding the derivative much, much easier. So till then, I will catch you in the next video.